Hi, everybody. My name is Jonathan Sukovich from the University of Michigan, and today I'm going to be talking about transmit-receive capable histotripsy transducer systems for real-time treatment localization and mapping and evaluating induced tissue damage. So real-time localization and mapping of histotripsy-induced damage transcranially remains a challenge because MRI is too slow and clinically burdensome. You can't image damage regions through the skull using ultrasound, but you can use acoustic cavitation emission signals which encode the information you needed to do all those things. And so what acoustic cavitation emission signals are essentially is when you nucleate a bubble with histotripsy, the bubble emits a shock wave that travels back to the histotripsy array, and then you can use the histotripsy array elements to measure the received ACE signal. And we've demonstrated the feasibility of using this transmit-receive capable histotripsy systems to capture ACE signals transcranially before. And we've shown that through a little bit of signal processing, you see the ACE signals up here on the right, and back projecting the signals into the field, you can generate image form the volume to see the skull and the cavitation bubble. And when you use these results to localize the bubble, they work out to be within about 1.5 millimeters of the actual positions of the generated bubbles. And we've demonstrated that we can do this localization at rates of up to 70 hertz. But the generation 1 transmit-receive systems were pretty limited. And so the received signals were nonlinearly compressed, which gave us a big dynamic range, but the low end sensitivity was poor and we didn't have any gain controls. So we weren't really able to measure weak signals generated near the periphery of the skull. And so that really limited us to only localizing bubbles in the central region of the skull. And we also didn't have a very long recording duration, which meant we could only capture the ACE signal emitted during bubble growth and not collapse. And you kind of need both of them to assess induced damage from what we've seen. And so we've constructed a new set of transmit-receive histotripsy systems. And so what you see here is the next generation transcranial histotripsy system. It's got 360 fully transmit-receive capable array elements. The whole thing is controlled by a Python scripting UI that's pretty easy to use, and we can communicate with it using Ethernet. So we can, transfer the data in real time to do the localization and mapping that we need to. Some specs about this system: it's got a 700 kilohertz center frequency. Peak rarefactional pressures at the focus are about 600 megapascals. There's 10 nanosecond transmit resolution, and it's got a steering radius of about 30 millimeters through the skull. On the receive side, the ADC is 12 bits. We've got a sampling frequency, adjustable sampling frequency that we can set anywhere from 3 to 50 megahertz. The max acquisition duration, depending on sampling frequency, is between 650 and 650 microseconds and 10 milliseconds. The ADCs have a variable gain amplifier with a 37 dB range. And we also have a high-speed toggleable attenuator that we can toggle within about 5 microseconds. That'll let us knock down the skull reflection signal, but then turn the gain back up to see the ACE signals that are transmitted through it. And so some example waveforms of the ACE signals that we acquired using the array elements. What you see here are the ACE signals associated with the nucleation on the left and the collapse on the right for bubbles generated in the free field. The ACE signals during nucleation are bigger and broader, but the ACE signals during collapse are more compact, so it gives you a bit better localization ability. We wanted to demonstrate the ability to do the localization and mapping through the skull using this system. So we ran some experiments where we placed tissue samples at the center of the array, treated it through the skull, and then used the ACE signals to map and monitor damage. And so we generated these cavitation events in bovine tissues, including blood clots, brain and liver, but due to an experimental error on my part, had to do the brain and liver in the free field. So really the only one that had transcranial is the blood clot. The treatment volumes were steered through 1 centimeter diameter volumes, and then the bubble lifespan was evaluated based on the growth and collapse ACE signal timings, and then damage in the tissue was assessed morphologically after treatment. And so what you see here are some results of those treatments in the brain and the liver. Again, these are in the free field, but you can see that the collapse time of the bubbles increases as treatment increases before saturating in both the liver and the brain tissue. And after treatment, you can stick a syringe into the treated volume and extract the emulsified volume. And what you observe is that the volume that you abstract from the treated tissue is equal to the volume of the region where the saturation in the collapse time was observed based on the mapped results. So transcranially, like I said, I was able to treat these, the clot transcranially. On the left here, you see a projected image of the ACE signals from the collapse event from a series of different pulses. And you can see that the collapse time of the bubble and the clot increases following the same asymptotic trends that we saw in the liver and the brain tissue. And through the skull, you can see that the signals are a little bit noisier, but the collapse signal is still big and compact and easily identifiable. Projecting those ACE signals into the field, you can generate image form the volume where the cavitation event was located. So on the left is the transverse plane image of the projected ACE signals. On the right is an projected intensity of the ACE signals in the axial direction of the array. And so the 3dB volume of this is about 3 or 4 millimeters, so fairly compact for no aberration correction. But anyway, the generation 2 systems are a great improvement over the generation 1 systems. We have a 3 times increase in focal pressure, much better low end sensitivity, and all of the receive settings on the system can be set on a per channel basis, which is really nice. We're able to detect the ACE signals transcranially, and the projected amplitude maps give a highly compact projection of the localized bubble. In the tissues, the lifespans of the bubbles increased asymptotically, and we saw that the saturation happened depending on tissues after a different number of applied pulses, but that the extracted homogenized volumes conformed with the volumes where the bubble lifespans in the mapped regions of tissue were observed to saturate. So that's a good indication we can monitor damage through the skull. And after that, I would like to thank everybody in the lab and take any questions.